Hello and welcome to this low-level JavaScript series on building Parser Combinators from scratch. This is the 7th and the final episode in the series, and you can check out the rest of the episodes in a playlist which is linked in the description below and on the screen now. Today we're going to build some of the more fundamental binary parsers, including a parser for reading unsigned numbers, a parser for reading signed numbers, that is, those that can be positive and negative, and a parser that reads raw strings, where we interpret each byte as a character. That's going to take us into bitwise number operations, binary encoding of positive and negative, and some of the tricky traps you might fall into when you're working with the binary number operations in JavaScript. And by the end of the episode, we'll be able to build a simple parser for a binary data structure, which is an IP packet header.
Now, before we really get going, I first need to fix something from the last episode. There was a simple typo bug that I didn't notice at the time, but unfortunately it's the worst kind of typo bug, which is the one that actually works in some cases. So if we look here in the bit parser, where we are trying to extract the byte offset, we actually just use parser instead of parser state. Now, because we use parser.index, that is going to evaluate to undefined. That means that when we run this whole expression, and I'll run it here in the node REPL, we're essentially doing this, which of course when you run that is not a number, because undefined divided by 8 is not a number in itself, and if you floor that, it's not going to change. So the question is, why were we still able to successfully read a byte? Well, the answer is that we were trying to read from an array buffer data structure. And in order to read from an array buffer data structure, you need to use a data view. And this is what we're doing here. This is the target we actually passed to the parser. But for a reason that eludes me, the data view, when passed not a number, will instead read the first byte that it can, or the first piece of data that it can. So it just treats not a number as index 0. And that's how we were able to not see this in the previous episode. But in any case, let's just fix the reference in all three parsers we wrote and move along. Okay, so today we're going to build 3 parsers. In order to parse our packet header at the end, we're only going to need one of them, but we're going to build all 3 because they are the 3 most common binary parsers you would need to parse binary data structures. So the first is the Uint parser, unsigned integer. And we're going to write a general parser in this case. It's going to take n bits, and it's going to return, for example, a new parser. So we're going to read n bits, and we're going to interpret those n bits as an unsigned integer. And likewise, we're going to do the same thing for integer. So in this case, the number would be either positive or negative. But we're still going to read n bits, and we're still going to interpret those n bits as a number. So when we're talking about n bits here, we're basically talking about maybe I want to read a 3-bit number, or maybe I want to read a 16-bit number. And in both of those cases, this gives us the flexibility to do that. Finally, the most useful last parser we could write is a raw string parser. And in this case, we would take an S, which would be the string we want to parse. And then what we would do is we would extract 1 byte for every character in the string, and we would check if the character code of that string matches the byte that we've parsed. This kind of parser is very useful because the beginnings of many binary files, the first few bytes, are actually an encoded string, the so-called magic string, which says something about what kind of file it is that you're parsing. So we're going to start with Uint because it's simpler than integer, and it will illustrate to us the basis of the idea. We're actually not going to return just a new parser here because, like I said, we're going to extract a sequence of n bits, and then we need to do something with those bits. So we already have the tools we need to extract a sequence of things, and we want a sequence of n bits, so we want an array of bits. We can actually generate an array of exactly that many parsers with array.from. We can pass here at the n, and we can use the second argument to indicate that we always want to get a bit. And then when we've extracted that information from the parser, we can map the bits that we receive. And what we want to do with these bits is we want to reduce them into a single number. Right now we have an array of n bits, but we want to interpret those as one number. So we can use array reduce for this. If you don't know too much about what reduce is doing, well, you can read the text that's in this box here, or you can read on MDN or something, but it's basically a generalized map function. But instead of mapping one element to another, it lets us translate an entire structure into another structure. Now, we're going to use reduce to collapse an array into a single number, but we could use it also to translate an array into an object or some other kind of data structure, which is based on the contents of the array. We're going to have our accumulator value here as the first argument. The second argument will be the bit. And we're actually going to use the third argument, the index, as well, because the position of this bit is important. And we need to start out with the value 0 because we're adding up. So we need to take whatever is in the accumulator and add to it the value of this bit. And bits just represent powers of 2. So the first bit, if it's a 1, represents a 1. The second bit, if it's a 1, represents a 2. And the third bit, if it's 1, represents a 4, and so on. And so we need to shift these bits into position. So we could do something like this. But in the last episode, we shifted the bits and we were reading them from left to right. And so we had to offset I. And because we read the bits in the other direction, now we need to flip it again. We need to shift them in the other direction because we haven't read them in the order that we might expect. We're not dealing with the first bit, we're dealing with the last bit. We actually need to offset this. And we need to offset this by n minus 1 minus I. Now, why n minus 1? Well, in the last episode, we offset by 7. And 7 is just 8 minus 1. But in our case, we have a generalized function. We're not dealing with a single byte. We're dealing with an unknown number of bits. But the thing is the same. We're still just dealing with n minus 1 things, minus I. So this should allow us to extract an unsigned integer. Let's try this out and see if it actually works. So we already have a parser here. Let's replace this with uint. And let's just read a single byte. So if all goes well, we should read the byte 234. Let's come out and try this. And we were indeed able to read the byte 234. Now, let's not make the same mistake 2 times. Let's actually read a sequence of 2 bytes. And let's see if we're able to read 235 as well, since we have that as sort of the second byte in our buffer. And we see, indeed, we are able to read both bytes out. It wouldn't be much use to us if we could only read bytes. We should also be able to read different values of bits. For instance, we should be able to read the first 4 bits of this number. Now, we can see what the first 4 bits of this number would be if we take 234 and we convert it to a binary number. And we take these first 4 bits and we evaluate them. This is the number 14. So we might expect that if we read the first 4 bits, that we would get the number 14. And if we read another 4 bits after that, we should expect to see the second half of the number, which would be the number 10. So we should expect to read 14 and 10. So let's give that a try. So here we see 14 and 10. It's great. And let's just do one final check. Let's see if we can actually read all 16 bits of our array here. So these 2 numbers combined. We can see what those 2 numbers would be combined in the same way. We take 234, and then we take 235. We get their string representations and we add them together. If we evaluate this number, we should see 60,139. Great. But there are actually some edge cases here that we're not dealing with. I mean, an obvious one is that n could be less than 0, or less than 1 even, and that doesn't really make sense to try and read a number that doesn't have at least 1 bit. So we could sort of throw an error in these cases, because it's just a nonsensical way to use the parser. So if n is less than 1, we can at this point just throw a new error in uint. N must be larger than 0, but we got n. And if you're wondering why we're throwing an error here rather than returning an error, it's because this is not an error that's occurred in parsing. This is an error that's occurred because the user has used the library wrong. So at this point, we want to throw the error as soon as possible. So this will happen at the moment they actually declare their parser. Now, that's not the only edge case. There's actually a second edge case here, which is more subtle. And that is that the number in JavaScript is a 64-bit double precision floating point number. And that sounds really fancy, actually, when you say it like that. But that's not a very exact number. That kind of number is a trade-off between how well you can represent floating point numbers and how many numbers you can actually represent. And you do run into these problems when you're trying to use this number purely as an integer. And not only that, JavaScript has some legacy attached to it, where if you try to use bitwise operations, like we're using here, this number will always be cast to a 32-bit signed integer. And that is not useful for us, because if we try to pass any bits which are too large, we're not going to get the values we would expect. So if we try to pass a large integer here, we're simply going to be out of luck. Now there is a solution around this, and that is the big int number. And the big int is a special kind of integer which has been introduced in JavaScript. It allows us to represent integers to arbitrary precision, so we can have arbitrary length of integers. And this will allow us to perform bitwise operations safely. So what we can actually do is we can convert here our bit into a big int. So we have a 1-bit big int. It's not extremely useful there, but it does allow us to perform this whole operation in a way that we can be assured that we don't lose any data. And then we have to convert the whole thing back into a number in the end, because we could have big ints as the primary number of this library, but I'm going to choose to make the trade-off and use the regular number, simply because it's a little bit inconvenient to work with big ints, because they're not the native number. So they're unexpected. They're not what you would think of in a library, I'm going to go with number, but I'm also going to limit n to be less than 32. Just so that if we want to parse numbers that are greater than 32 bits, that we have enough buffer and that we can use we can use a special parser or perhaps build an edge case into the library using big int. But I would like that to be more explicit and to have an understanding that you're going to receive a big int number on the other side. So for now, I'm just going to put a limit in the library. All right, so let's move on to the integers. Now, the integer, it's actually going to be very similar to the uint, so it's going to be similar enough that I'm going to copy the uint. Now, we need to just stop and think about the integer for a moment, because, of course, since the integer can represent both positive and negative numbers, it needs some way of encoding the fact that it's a negative number. There's nothing about a binary number that natively describes that it is negative. There's many different ways of doing this. Let's say we had the number 1 in binary, and we'll use 4 bits to keep it simple. How could we illustrate that this number is negative? Well, one way that you might think of is just to say that the first bit is going to illustrate the sign of the number, whether it's positive or negative. So if it's a 1, then it's a negative number. The other 3 bits we'll use to represent the value of the number. So that means we're limited on how far we can count. We can't count as high as we could before, half as high actually, but now we can go half in the positive direction and half in the negative direction. Now this actually works well enough. You could do something like this, and we would expect this to be the number -1. But have a little look at this phenomenon. Let's say we have the number 0. What is this number? Well, intuitively, you'd have to say it's -0, but of course, there's no such thing as -0. It's not really an actual thing. But in this number system, we end up with 2 zeros. It is a strange phenomenon. And not only do we end up with 2 zeros, our addition doesn't work like we would expect it to. So if we have 2 numbers, let's say 1, and we have -1. Now, if we want to add those 2 numbers together, the way you can add binary numbers together is just like you learned how to add decimal numbers at school in this table, and you come down, you start on the lower place, and you add the 2 together. If their result is greater than 1, then you need to carry the result to the next column. So here we have 2 1s, that means we get a 0, and we carry to the next column. So now we have here 0, 0, and 1, so we've got a 1, we get rid of our carry, 0 and 0 is 0, and 0 and 1 is 1. But this number is -2, of course, because we have 2 here in the value, and we have a minus here. And we know that 1 plus -1 is not 2. So addition is compromised in this system. This system is called the ones complement. And it is still a valid way of encoding binary numbers. Like, it has advantages. It's very simple. It's very direct. But it has the disadvantage that if you want to work with the number afterwards, then you have weird effects. And also you have 2 zeros, which is unusual. There's another system we could use, which is called the twos complement. And that's the one that is typically used because it has the nice properties that we're looking for. Now, in twos complement, regular numbers are the same. So this is still 1. Negative numbers, instead of just simply flipping the bit to indicate that it's a negative number, instead you go through a small algorithm. So to get -1, what we do is we take 1 and we flip all the bits. We would get this number where we flipped each 0 to a 1 and each 1 to a 0. And then you simply add 1, which of course would give us 1, 1, 1, 1. And in this system, we would consider that number to be -1. So let's take another number. Let's take the number 4. Let's turn that into its twos complement negative version. So let's flip the bits. Let's add 1. We need to add these 2 1s. We get a 0, but we carry. 1 plus 1 is 0, and we'll carry that again. Here we get 0 plus 0, so we can put our 1 down. And of course we have a 1 here. So this number is -4. Now, like I said, this system has the advantage that addition actually still works in the same way. So if we wanted to take -4 and we wanted to add 1 to it, we could easily do that. So let's add 1 to this. And the end result that we would expect, of course, is -3. So this is our number, and this is indeed the binary encoded number for -3. But you might actually think, oh, but that number over here is 5. Well, this is not like ones complement. This part, when the number becomes negative, this no longer means the same thing. Basically, this is where the main trade-off is, in that actually reading the number as a negative number becomes a little bit more challenging. And we can even see this system working if we run it in the node REPL. So if I come over here and we take a number like 4, so 0, 1, 0, 0, and we flip all of its bits, and we can do that with the tilde, which is the unary operation to flip bits. We'll get -5, and of course if you add to 1, you get -4. So we actually end up at the negative version of 4. Now this works because, like I said, bitwise operations in JavaScript, they act in a certain way. For one, they immediately are cast to 32-bit signed integers, so this will work, just because 4, even though it's a 4-bit binary number here, we're actually operating with 32-bit binary numbers, but the math is the same. And secondly, these operations, of course, they operate within a specific set of rules, so they don't adhere to the normal number rules where the actual underlying number, as we've discussed, is a 64-bit double precision floating point number, and this is not actually the binary representation of that kind of number. It has a different binary encoding. Much like 2's complement is a system that complicates regular numbers, the floating point system goes even further with that. But at the very least, we have a system that works, and we know that we can perform these operations to get these encoded values back into the weights we need. This isn't enough for us to round this whole system off. We still need to massage the data a little bit to get it the way we need it. So if we scroll down, we can begin to implement the integer. Now, we still need to check for errors. We still need to get a sequence of bits. And then afterwards, we need to somehow accumulate the bits. Now, luckily for us, the leftmost bit still actually does indicate if the number is negative or not. So if that number is a 0, if that leftmost bit is a 0, then we know the number is positive, and we can actually just use the normal method for turning that back into a number. So we can just perform a check here that if the bits is a 0, just do what we were doing before. We only need to do something different if it's a 1. Now, if it's a 1, then we need to somehow get the bits into a different position. And let's just go back over to the node console for a moment and think about how this might look. So if we had the negative number 4, I'm going to put it inside this array. So this is not negative yet. We need to flip the bits, and we need to add 1. We would end up with these bits. Now, what you might notice is that if we just remove that last bit, then this 100, it is still 4. And we could just manually strip off that bit, work out what the number is, and apply the minus sign, and we would get back to -4, because we already know that the number is negative. So why don't we just try that? We know that the bit is a 1, and we need to flip this bit. A simple way we could do that is to just check if the bit is a 0, and then if it is a 0, we flip it to a 1, and if it's a 1, we flip it to a 0. And now all we have to do is to add 1 to the final result, and then make the whole thing negative. A little bit of a convoluted formula, but it should work. So now we can scroll down and change what we had here, and we'll grab an int 8, so we'll get a single byte. And because we have a number here which is greater than 128, that means we know that it's going to be a negative number. We can work out which negative number this should be by coming in and just finding the binary representation, and then going through this algorithm. So we'll take our binary number, we'll drop the first bit, we'll flip all the rest, and we'll add 1. And so we should get -22 in the end. So let's give that a go. And here we see -22. Great, so we can be fairly assured that our negative numbers are working. So that leaves us with the raw string. Now, raw string is actually pretty simple. Let's even copy integer here, because it's going to have some similar edge cases. So we want to check that we have a string with at least 1 byte in it, so let's check the length of s. We're not going to put a particular limit on the string, and instead of returning this whole sequence operation, the bytes that we want to get are s.split. We'll split the string into an array, we'll map over the array, we'll get the c, and we'll simply say c.char code at the 0th index, and that will give us the numerical representation of this number, and that will be the same as the byte. So now we have an array of bytes, but what we need is an array of parsers to give the sequence of. So what we can do is to actually map this a second time, and we'll map these numerical values into parsers that get these specific numerical values. We get the number that we got out, and we want to return a uint 8. So we want to capture 1 byte. But I actually want to assert that that uint 8 should be a certain number, and I want to fail the parser if we're not able to get that. Now, we're going to need to add something to our library. And I'm going to scroll down, and here we're going to write 2 more parsers. So I'm going to have one called fail, which is going to take an error message, and then it's going to return a new parser, which takes a parser state. And all we will do here is return update parser error. We'll take whatever state we had, and we'll update it with the error message. And the flip side of that is that we have a parser called succeed, and that just has a value. And here, instead of returning an error, we just update the result with the value. Let's return those two from our library. And with those two parsers in hand, let's go back to the code. Let's bring these in, fail and succeed. And now what we can say is that when we are able to get our 8-bit byte, we can use chain to get the result of that. And here we can just check the result, and we can say if the result is equal to the n that we expected, then that's great. We'll just succeed with n. And otherwise, we're going to return a fail. And we can use the message raw string expected character, and here we'll go the other way. And this works, of course, because chain is all about letting us define what the next parser will be based on the previous parser. And succeed and fail are both parsers. It just so happens to be that they don't actually do anything with the data, and they don't move the data forward. So this is still valid, but the only thing those two parsers do is either cause the result to be a failure or cause the result to have a certain value inside. And in the case of succeed, we're actually not changing the value at all. We're just keeping what we had before. And in the case of fail, we're able to give an error message. But now we have byte parsers. And so what we can return here is just simply a sequence of byte parsers. And depending on how you want to handle this, you might want to say that raw string just always returns the string that you passed in. You might want it to return the bytes. In this case, I'm going to have it return the bytes. And let's try that out. Let's put a raw string here. In the U88 array, we could actually just construct a string that we know is a byte string. So we'll take the string hello world, split it, and map it in the same way. And that will produce an array, which will be consumed by Uint8 array, and we'll get the buffer from that. And of course, we need to match a certain string, and that string will be hello world. And here we're able to extract the bytes. Now, let's rest assured that this is indeed hello world. But if we were to change something here, we should see a fail, and we should see we expected character Z, but we got D. So we know this is now working. All right, and with all of that, now it's time to actually come and parse our data structure. You might remember from the last episode this diagram of an IP packet. This describes the bit locations and the bit widths of all of the different pieces of data that this header contains. Again, we're not going to concern ourselves too much with what each individual part is. We simply want to extract the data and get it into a useful form. So preferably, we would have an object which had keys with each of these things, and we were able to access the value in a really easy programmatic way. Now, I have a data structure prepared here. It's called packet.bin. So let's just write the parser that we would hope to use for this data structure. It's of course going to be a sequence because it's just naturally a sequence of bits and bytes. And the first thing that we want is the version, and it's 4 bits. And it's going to be an unsigned integer of 4 bits. And what might be useful for us in the end is to take each of these and tag them with the name that they have. So just put them in an object with a name so that we get the name and the value together. So I'm just going to write a small function here called tag. Tag is going to take a type, and then we're going to curry it, and we're going to take a value, and then we're just going to put those two things together in an object. And then we can simply use map here with tag and pass it the type, and map will give it the value later. So let's say this is going to be a version. Okay, and now we can just go through and do this for the different data. So we would have IHL next, then we would have 6 bits for the DSCP, 2 bits for the ECN, and then we're going to have 16 bits for the total length. Next we have identification, it's also 16 bits, 3 bits of flags. That leaves us with 13 bits for this fragment offset. The time to live is a byte, the protocol is also a byte, and the header checksum is 2 bytes. And then finally, we have 32 bits that represents the source IP address and 32 bits which represents a destination IP address. There is actually an extra piece on the end, but as we can see, this is only if IHL is greater than 5. So let's just see if this parser even works for us in the beginning. We're going to obviously need to read this file. So what I'm going to do is I'm going to scroll up to the top and I'm going to bring in the FS module for the file system and path. Just for illustration purposes, I'm going to read the file synchronously. You shouldn't do this in real applications. You should build actual infrastructure around, but for this, I think it's fine. So let's read the file synchronously. The path is going to be the directory name of this file and packet.bin. And since it's a binary file that we're reading here, we don't actually need to supply an encoding. We will automatically be given a buffer. Now, I'm actually going to put a debugger statement here, and we can see the file that comes out. So something obviously went wrong. Path is not a function. It should be path.join. So let's try that again. And then we can look at this file. And this file was actually of type buffer. Now, we need an array buffer, but luckily for us, the buffer is actually built using array buffers. So there is a buffer property on this file, and we can use that buffer to get an array buffer. So after we've read the file, we get the buffer. That gives us the file. Just like before, we need a data view. So we can actually move that up, and we'll make a data view out of our file. And then it's just a case of getting a result out of the parser. So we can take our parser, we can run it on the data view, and we'll console log the result. Get rid of this debugger statement. And now we see our table here. Although we have it in an array, we have the types and the values. So let's go in and check if these actually make sense. So we have a version, it was 4 bits. So that means it's half of this byte, and it's the number 4, which we see here. For IHL, we also see the number 5. That's great. DSCP was 6 bits, which means it's this half of the byte plus the second half of this, which we obviously can't split up here in this display, but it's all zeros. So DSCP is 0, and the remaining 2 bits of ECN is also 0. And that makes sense because we see 0, 0 here. So next, the total length is 2 bytes. So that would be 2 bytes here, 0044. Well, let's just get the node so we can evaluate that number in hex. That's the number 68 in hex, and we see the number 68 here. Identification then is another 16 bits, and that's going to be AD0B. So AD0B, we see 44,299, and we see the same thing here. Flags was 3 bits, so almost most of this half of the byte. We can't see it, but again, it's a case where we have 0 here, and the fragment offset, which is the remaining 13 bits. So that is going to be these remaining pieces plus 1 bit from here. We actually have zeros there, so we would expect a 0 here. Time to live is 1 byte, byte 40, and that's 64. We see 64. The protocol is also 1 byte. That's hex 11, and hex 11 is 17, so we see that. Header checksum, 2,298. That's going to be 7272, so we get what we expect. And then finally, we get to the IPs. Now, this is not how you're used to viewing an IP address, but an IP address is made up of 4 individual pieces. So we would have the first part, which would be AC, and we had to have the second part, which would be 14, the third part, which would be 02, and the fourth, which would be FD. And this is more of a typical looking IP address, 172.20.2.253. Now we can check that that is actually the number when we put all of this together if we just don't split it up, but we have one continuous hexadecimal number. And here we see this long number, and that is the same as the number here. And finally, the destination IP, it's the same idea. We need to get this in hexadecimal. And this number is the same as this number. So we were able to pass those successfully. And you might actually want to come in here and turn these two into a sequence of 4 bytes in order to actually pass that in a more human readable way, because this is the main part of the data structure. But we can see that we were able to extract the data. Now, like I said, there is a little bit more, which is if the IHL was greater than 5, we actually don't have a value greater than 5, but we should be able to extract it if we do. Now, what we can do is we can come down, we can use chain, we get the result of what we got, and we can just check here if the IHL, which is the second element of res, is greater than 5, then we want to get the rest of the information, and that's going to be the option. So basically everything else. Now, the res is actually the header length. So up here we would see header length is 5 times 32 bits, and that gives us 20 bytes. And everything we've passed up until this point is 20 bytes. If you add all of this up, you'll find 20 bytes. So everything after this is the rest of the bytes. So what we actually want to do is to say that the remaining bytes is res1 minus 20. And then we can use this to build an array which will pass that number of bytes. So let's use array.from. The length will be the remaining, and we will extract a uint 8. And then what we can do is return a sequence of the remaining bytes, and then we'll use chain in order to give us back the rest of the result. So we'll take the remaining here, and we'll just return a new array where we spread out the old result and a new tag, which will be what's called the options. And options is curried, so we need to call it in this way, and we'll call it with remaining.
Except, of course, that actually this res should be using the value. Since we've created this tagged object, we should be accessing the value property, and we need to do that here as well. And I think that is all we need there. And now it is complete structure. I want to give a massive shout out to Ben Eater's channel. He has a whole series where he builds an 8-bit computer from scratch on breadboards, and he goes into far more eloquent detail than I could possibly ever about binary encodings and the way that bits are moved around and interpreted. And I think it would make an excellent accompaniment, and everyone should go and watch that. I really hope you've enjoyed this series. If you have any feedback, of course, I'd love to hear about it in the comments or in the low-level JavaScript subreddit. All the code is available on GitHub, and you can find the repository also linked below. Thank you so much for sticking around and watching all this time. I've got some really cool stuff planned for this channel, so subscribe to be notified of new episodes when they come out. Thanks for watching, and I'll see you next time.